recognition. He got his PhD at the University of Michigan in '74, and he has been working on developing an embodied theory of language comprehension. He will talk to us about premotor cortex, action control, and language.
So, would it be possible for people in the back to move up? No, that's impossible. Okay, so I'll try it this way. So, indeed, I'm going to try to relate those three areas, and because I am picking up on many of the points that Luciano made the other day, maybe the subtitle should be, whoops, homage to Fadiga. So, but he is not here, so I'm going to take that away. Excuse me? Ah. Okay. So, for those of you who don't do action control, let me just start out by saying that, in fact, action control is amazing. And why is that? Well, just consider what it takes to hit a tennis ball or to play the piano or even just to walk down the steps like this. You know, what's involved there? So first off, we have coordination among muscles. And I don't mean just one or two muscles, but coordination among tens and 20 and hundreds of muscles to get that tennis stroke at just the right point. Or even just to get your body up the stairs without falling over. Certainly, we have hierarchical control over serial order in action like that. We have continuous recalibration. It's not that I can learn how to walk up and down the stairs just once. I have to recalibrate my steps for just about every staircase that I go on because of the height of the risers. I have to recalibrate my steps depending on how much exercise I've been doing and how much fatigue that I have in my muscles. The timing has to be exquisitely precise, perhaps down to the millisecond so that I don't tumble down those stairs, certainly down to the millisecond to play a concerto well or to hit a tennis ball well. And all of that precise timing has to be in the context of slow sensory feedback. That is, there's not enough time to allow the proprioceptive signal to go up from my finger up to my brain before I have to make the next response. And sometimes, of course, the feedback is irrelevant. The point is that evolution and the brain have done a wonderful job solving a set of very tricky problems. What I'd like to suggest is that maybe those solutions can be used to solve other tricky problems, such as tricky problems in language. After all, in language, we have hierarchical control over serial order. We have things like continuous recalibration. We have precise timing, and so on. Well, here's what I'm going to try to do in today's talk. First, to sketch for you one solution to action control problems, namely controller predictor models of action control, otherwise known as forward and inverse models. And I'll be focusing on Wolpert's hierarchical mosaic model. And then once I do that, I'm going to try to relate the hierarchical mosaic model to the brain, particularly using canonical and mirror neurons. I think the neuroscientists in the crowd will find this unsatisfying because it's only the grossest relation between the computational model and the brain. And then I'm going to try to show you a marvelous confluence, namely that the hierarchical mosaic model of action control with minimal changes can be a model of language learning, production, and comprehension. Why not try to do everything at once? And I think probably the linguists in the crowd will find this embarrassingly naive, but at least I hope it's a sketch in the right direction. And then finally, I'll have data from several projects testing some of the claims that language comprehension is intimately related to action control. And finally, I hope to satisfy somebody, and that would be the psychologists in the crowd. Unfortunately, there are probably only 2 or 3, so we'll see what happens. Here's the Wolpert mosaic model. It's a model designed to handle action. And so let me give you an example. You know, suppose that, thank you. Suppose that I have as a goal to pick up that bottle, okay? And so according to Wolpert, what happens is that that goal in terms of a trajectory is fed to the controller model right there. And what you should be thinking about in that controller model is that it's a small neural network. And that's what the circles and the lines is supposed to represent. So we have a small neural network that, given the goal of that trajectory and the lifting, will send a signal out to my body, out to the periphery. It's very hard to judge if that bottle is full or empty or half full. How much force should I use in lifting that bottle? Well, in fact, it's given the input here, it's very difficult to decide. And so what Wolpert suggests is that, in fact, the amount of force that's sent to the body is based on an integration of various possible pairs, various possible controllers. So a controller for lifting 500 grams, a controller for lifting 350, a controller for lifting 150, and so on. Now, those controllers, the outputs, are integrated using what Wolpert calls responsibility signals. And a responsibility signal is a guesstimate, a probability estimate of which context you are in. Namely, am I in the context of an empty bottle, a full bottle, or a half-full bottle? And although those responsibility signals are intimately important for this model, in fact, I haven't illustrated them at all. You're just going to have to trust me that Wolpert has worked out the mathematics for how those responsibilities can be learned and used in the rest of the model. So we have an integration here of the output from various controllers that's sent to the body, but also that same signal that's sent out to the body is also fed back into these predictor models. And what those predictor models then do is to generate a prediction as to what the sensory consequences will be when I apply that integrated force to lifting that bottle. So for example, the 150-gram predictor says that, you know, I'm applying too much force, and it's going to go like that. Whereas the 500-gram predictor says I'm applying too little force, and in fact, I'm going to slip, okay? And so we have those predictions from those predictor modules. So what are those predictions good for? Well, they're good for several things. One, those predictions of what we're going to get can give us a type of feedback, a pseudo-feedback, that's faster than the feedback that we will get from the body itself. Second, those predictors will select the relevant feedback. What should I be paying attention to when I'm going down these stairs? I should be paying attention to some, for example, some of the proprioception, paying attention to some of the visual signal. I shouldn't be paying attention to what's going on out there in the crowd. And so the predictors essentially tell me what I should be attending to. the predictor helps learning of the controller. And in fact, it turns out that computationally, these models have to work by first learning the predictor and then learning the controller. You can see there are several reasons for that. One, once the predictor is predicting accurately, well, then the controller can be learned offline, as it were. Second, what we're going to see is that the learning by the controller is produced by an error signal. Let me just do that first. So what happens is we take an action. That action then does provide feedback. And the feedback, the sensory feedback, is compared to the predictor. And the difference between those two generates an error signal that then is used in learning the predictor, in learning the controller, and learning those responsibilities. I know, after I start lifting it, what context I'm in by comparing the actual feedback to the feedback of those various predictor modules. So when we have a predictor that's predicting accurately, well, then the difference between what the predictor is predicting and the actual feedback can be learned to, can be used to learn the controller and to learn the responsibilities. So that's the basic Wolpert mosaic model. I want to add to it one more factor. It's not me in particular. This is something that's been added to this model by Rick Grush in a BBS paper and also by Susan Hurley in trying to get this model to be a model of imitation. And it's the idea of gain control, namely that we can shut down on the actual, the overt instantiation of those motor commands to the body. And so we have the controllers being integrated, generating a command about how much force to put on that bottle. But when gain control is set low, then I don't take the action, but the efference copy is still fed back into the predictors. And what we get at that point is a model that can be used for planning. We get at that point a model of imagery. That is what we would expect from the sensory, from the environment, if we were to actually take that action. So here's the basic mosaic model along with gain control that's going to be turn out to be important for language. Now, Wolpert takes it another step. He talks about a hierarchical version of the mosaic model to handle things that are a little bit more complicated than just how much force I should put in lifting that bottle. So for example, what does it take to drink? Well, Wolpert says that there's a basic motor repertoire that corresponds, I think, to what Luciano was talking about as motor repertoire words. That we would probably find in motor cortex, how to move the eyes, how to extend the arm, how to grasp, how to lift. And so, whoops, sorry. So all of these are sets of controllers and predictors for moving the eyes, extending, and so on. But what's happening at a higher level in the hierarchy is also a controller and a predictor for how to combine those to do something like drinking. And the way the controllers and the predictors work at that higher level is not by generating action directly, but by generating a vector of probabilities, a vector of prior probabilities. For example, what's the probability that the next thing I'm going to do is move my eyes? What's the probability it's going to extend, the grasp, and to lift? That vector of prior probabilities, the highest probability is fed back as an efference copy to the predictor. The predictor predicts the posterior probability that I'll actually be moving my eyes. Once that's set up, well then if the highest probability is indeed to move the eyes are moved. That generates feedback from moving the eyes. The feedback updates the hierarchical controller and predictor, so that now the priors are updated to extending the arm, and then the extension happens. There's feedback from extension, and so on. And so what Wolpert has done is to show that this sort of hierarchical model can learn on the basis of the feedback error and can learn to take various complex actions. So what does this have to do with language? Here's where I want to take a couple of jumps past Wolpert, although as you'll see, it's not many jumps past Wolpert. The first thing I want to do is to talk about those controllers and predictors as being in Broca's area and made up of canonical neurons and mirror neurons. So just to very, very quickly review from what you've been hearing before, canonical neurons and mirror neurons were first discovered in area F5 of the macaque, and then the canonical neurons seem to respond both when the animal, canonical neurons do respond, both when the animal is making an action and when the animal is observing something like this. It's as if the canonical neurons are saying what actions are possible, that is, the affordances of the situation. Mirror neurons respond when the animal is making the action, as well as when the animal sees a conspecific or a closely related species making the action. And it seems that the purpose of these, the mirror neurons in particular, are for action recognition, a type of theory of mind. They probably enhance perception and maybe for communication. And that notion about communication is enhanced once one considers the human data, partly that this area of macaque cortex seems to correspond to Broca's area, and data from fMRI and TMS, as well as behavioral data, seem to show that there is a human mirror neuron system that acts much the same way, not exactly the same way, but much the same way as the macaque system does. Interestingly, as Luciano reviewed, Broca's area clearly is not just involved with speech production, but also with things like control of the hand, as well as mathematics and music. People have been demonstrating very clearly that there's a close relation between language and action systems. We saw some of those data a little bit earlier. And I want to also remind you of some of Luciano's work showing what he has called echo mirror neurons, what I'm calling here speech mirror neurons, namely mirror neurons that respond when you are making an articulatory gesture, like a trilled R in Italian, or when you are observing, that is, hearing somebody else making that same sound. So I'm claiming that these controllers and predictors can be made up of canonical neurons and mirror neurons. What else do we need then to turn this into a model of language? Let's recall that Broca's area is certainly used during speech production. It's used for controlling the hand. That Fadiga has shown us the existence of these speech mirror neurons. What else do we need? Virtually nothing. Let's just say that, in fact, what's controlling speech are controllers and predictors that are in Broca's area and that are associated with the controller and the predictors for particular actions. How could that association arise? Well, if both of those things are in Broca's area, well, we have some of the preconditions for Hebbian learning, that is, for connecting up a representation of the speech signal with the representation of the actions that it describes. Note what this does. It uses this model for serial control of action, like going down the stairs, and says, hey, why not use it as the model of serial control in speech for how we get the d and the r and the ink in drink? Note what else it does. It gives us a bidirectional association of speech and action, so that when we are thinking of an action, such as taking a drink, we may actually be saying that to ourselves. Or, in fact, when we're talking about taking a drink, it's very likely that we're going to gesture. I don't mean an articulatory gesture here. I mean a hand gesture. And so what this model is trying to do is to show how the gestures that we produce automatically all the time arises. And finally, what this model attempts to do is to ground meaning. Truly, I've been amazed at how little discussion of meaning there's been at this conference. I mean, what do we think that language is about? Language is not about creating tree structures. It's not about syntactic manipulation. Language is about communicating with one another. It's about communicating meanings with one another. It's about coordinating those meanings so we can get things done in the world. And what this model is saying is that we understand the symbol drink because it is intimately associated with the actions of drinking. So now let me tell you some stories, okay? The first story is how a baby might learn the association between the word bottle and what a bottle is. So here's how the story starts out. The story starts out by assuming the child already knows how to interact with the bottle. The baby knows how to move its eyes to find the bottle, and then once it's found the bottle, it knows how to grasp it. Now, within this background, imagine a joint attention situation where the dad says to the baby, here's your bottle. Here's your bottle. Okay? Well, now the baby and the father are paying attention to the same aspects of the situation. The speech mirror neurons in that baby are picking up and at least coding roughly the phonology of the word bottle. At the same time, the baby's canonical neurons are firing, telling the baby what it can do in regard to that bottle. And we have set up the situation where we've developed an association between phonology and meaning. Essentially, we've set up a construction where the child has learned that the word bottle goes with the interactions that it already knows about with bottles. So it's learned the meaning of the word bottle. Namely, move your eyes till you find something that gives you the right sensory feedback and then grasp it. Let's tell another story about learning verbs. For example, how the child might learn the verb to drink. Again, let's assume that the child already knows how to drink so that this part is set up and this part is set up, and what we're concerned with is developing the right association between a speech controller and the action controller. And again, the story can be relatively simple at this level, at least. The dad says, drink your bottle. Drink your bottle, goddammit. I'm not going to sit here all day with you. Drink it. And at the same time, the child maybe perhaps isn't drinking. And so the father says, look, like this, drink your bottle. And at that point, the child's mirror neurons pick up on the father's action. The auditory mirror neurons have picked up on the father's speech. And again, we have a simple situation for Hebbian learning. Well, let's take this one step further. Really? No, that's not true. I started at 3 o'clock. I thought I had 45 minutes. Okay. Do I have 45 minutes? Okay, thank you. So let's see what we get with a sentence. So the dad says, give Dada the cup. All right, well, the child doesn't know what the word give means. Perhaps the child knows what Dada means, which would mean move your eyes over to Dada and get ready to interact with Dada. Perhaps the child knows what a cup, what the word cup is, and the child looks around for a cup and does what it knows what to do with the cup, namely to grasp the cup, and perhaps to drink. Dada says, no, no, give me the cup. Give me the cup. Child doesn't know what give means. And so finally the father goes, give me the cup. The father goes, that? What does the baby's mirror neurons do? The baby's mirror neurons code that action. And now finally we can get the baby in a situation where through some laborious repetition we have an association between giving a cup and the stimulus, give Dada the cup. Not the sentence, you know, not any sort of analyzed tree, but pretty much a raw stimulus of give Dada the cup. Well, what's going to happen next so first off, let me just point out some of the motor activity that goes along with give Dada the cup. The child has to attend with his eyes to the speaker. The child has to then attend to the object and set the kinematics for that object and grasp the object. Has to attend with eyes to the speaker again and then extend his arm to the speaker. So learning the meaning of this sentence is learning an awful lot of action and an awful lot of serial control over action. But let's suppose that that gets done. And next, the child hears Mama say, give Mama the bottle. Well, as the child hears give, everything is going well. This speech mirror neurons are activated. The controller is activated. The controller predicts what's going to happen next, namely that I'm going to hear Dada. Uh-oh. What happens is that the child hears Mama. And everything falls apart. Why does it fall apart? Because the child has made a very high probability prediction that I'm going to hear Dada, because all it knows is give Dada the cup. And instead of hearing Dada, it hears Mama. So now we have to learn all over again another version of give, namely we'll call it give two for give Mama the bottle. And then when the child hears give Lavinia the candy, again, the child will be predicting from give that I'm either going to be hearing Mama or Dada. When the child hears Lavinia, everything falls apart and we have to learn another type of give. Maybe this happens again for give Dada the candy and for give Dada the spoon. But now that we've learned some particular associations between sentences and give movements, let's see what happens when we hear give Dada the bottle. When the child hears give Dada the bottle, something that he's not heard before. The child hears give. Give, again, excites the speech mirror neurons. It excites these controllers. The controller generates a prediction. And, the controller generates a signal to the body that generates a prediction of what it's going to hear next. And what the child is predicting that I'm going to hear next is either Dada with a 3 out of 5 probability, or Mama or Lavinia. Aha! The child hears Dada. Okay, now on hearing Dada, in fact, the responsibilities for give 1, give Dada the cup, for give 4, give Dada the candy, and for give 5, give Dada the spoon are all increased. The responsibilities for this one and this one are decreased. And so what's the child predicting now? What the child's going to predict now is that either I'm going to hear the cup, I'm going to hear the candy, or I'm going to hear the spoon. But note that the predictions cannot be made with much confidence. Okay? The predictions cannot be made with much confidence. And then when the child hears the bottle, indeed the predictions are disconfirmed, but it's not a very high probability prediction. And my claim is when it's not a very high probability prediction, that control does not fall apart. Instead, this system of gives is still controlling behavior, but at the same time, when the child hears the bottle controller is activated. The child attends to the bottle, grasps the bottle, and now the child has done all of the things to update these give controllers and predictors, and the usual behavior can just follow. So because we haven't had a high probability disconfirmation, because we've had an object interacted with that fits with this control structure, in fact, the control structure can simply continue to work. And here is what I am claiming. In other words, behavior consistent with having learned an abstract double object construction emerges from integrating by responsibilities, by integrating actions learned for specific concrete situations. I'm claiming that syntax and compositionality emerge from action control. So let me tell you about some data. Okay? Clearly, I don't have time to go through all of this, so I'll just mention a few things. Let me start out with this question. Is it really the case that the child knows about drinking before learning the word drink? Is it really the case that the child needs to know the word bottle before, the concept bottle before learning the word bottle? Well, we don't know the exact answer to that, but we do have some correlational data that's suggestive. This is based on an analysis of the MacArthur-Bates Child Development Inventory, where parents fill out what gestures their children are capable of and what words their children are saying. And interestingly, nobody ever put those two together. And so what we did was to try to pair up the gestures in the MacArthur-Bates CDI with the verbs and to try to pair them up in some sort of sensible way, like maybe the gesture patty cake, this, corresponds to the verb clap, or the gesture for drinking from a cup corresponds to the verb drink. What I haven't read here, it just picked out pretty much randomly some that will illustrate in red on the next slide too, just to keep you oriented here. Well, is it the case that the gestures precede the verbs? Here are the data. There's an amazing correlation between the order in which the gestures are learned, given on this axis, and the order in which the verbs are learned. So the gesture for drinking comes in early, the verb for drinking comes in early, and so on. But what you might note is that there's a tremendous lag. There's an average lag of about a year between when the gesture comes in and when the verb comes in. Partly, you know about this. You know that children comprehend faster than they produce. But what's sort of interesting is that there's a computational reason in this model for why there might be a lag. Namely, as I mentioned before, the predictor has to do its learning. So the predictor about what's going to happen when I hear the word drink or when I hear the word clap, it has to be learned first before the controller that produces the speech can actually get its job done. And so the claim is that that lag, at least part of that lag, is the learning of this predictor, that is what the prediction is going to be when I hear the word drink, what I'm going to see in the environment, what's going to happen, and actually learning the production of the word drink. How much time do I have now? 7 minutes. Okay, 8 minutes even. We're collecting experimental data on this now, but I don't have enough data to tell you any story whatsoever. That is it the case that if you experimentally teach children a gesture, that they will be able to learn the name faster than if they've just observed the gesture? But here's another experiment that I really like a lot. I see this as my poor man's TMS experiment. Right? And you'll see why in a moment. It was actually inspired by the controller and the predictor for my knees. My knees used to be really good. I could run and I could bicycle and I could climb up and down stairs with great ease. And then they started to go. And now, when I look at stairs, just looking at those stairs, my knees say, don't do it. It's going to hurt. It's going to hurt. Please don't do it. Please. Or at the very least, grab onto a railing and go slowly because it's going to hurt. Well, so what does that have to do with any of this? What I think is happening is that by virtue of recalibrating, that my controller for stepping has sends out a signal, and the prediction is that it's going to hurt, and that by virtue of that, my controller has learned to go more slowly. Go slowly on the, wait a minute. If the controller for stepping is working more slowly, and there's this association between the speech for step, will my understanding of the word step be slower just because it hurts when I go down the stairs? Well, we decided to look at this experimentally. What we decided to do was to fatigue muscle systems and see if we could then show a selective change in the time to comprehend sentences that might call upon those muscle systems. The way we did that was by using cannelloni beans. We had people sitting, this is before any linguistic task, they're sitting down in front of the computer, and their job is to move 600 beans. It takes about 20 minutes. We chose that not quite randomly. We chose that because you get some evidence for neuroplasticity in 20 minutes of activity. We told people to bring their iPods and listen to music while they were doing this. Otherwise, it's awful. They're moving those beans one at a time. They're moving them either away from themselves, and away is defined by picking a bean out from this wide mouth container and putting it into having to aim for this narrow mouth here. Or we've switched the location of those two containers, and we had people moving 600 times towards themselves. Okay? And then the question is, will we see a selective change in sentences about movement toward and away? So let's look here at experiment 1, where we have people moving the beans toward or away. We give them concrete sentences that describe action towards them. Art gave you the pen, or action away, you gave Art the pen. We had abstract sentences about transfer of information. Liz told you the story, or you told Liz the story. We asked people to judge whether those sentences were sensible. Some nonsense sentences were thrown in, such as, Art gave the pen you. And people had to say that that was nonsense. What we're looking at here is how long does it take to judge the sensible sentence as sensible. Here are the data from this first experiment. And what you can see, it's particularly strong with the abstract, the sentences describing, there we go, the sentences describing the abstract transfer. Namely, if we've fatigued away systems here, we have slower judgments of the away sentence, you told Liz the story, compared to the towards sentence, Liz told you the story. Vice versa for when we let me start all over on that. When we have a towards sentence, we find that people are slower when they've spent 20 minutes moving beans toward themselves than when they've moved beans away from themselves. When we have an away sentence, people spend more time reading and judging that sentence when they've been moving the beans away from themselves compared to toward. Half the sentences were meaningful, such as you told Liz the story, half were nonsense. Yep, so they have to judge the meaning of the sentence. We see the same interaction for the transfer of information as the transfer of concrete objects, sentences describing concrete objects. For those of you who are thinking that maybe this is just some sort of lexical phenomenon, that we fatigue some sort of lexical representation of toward or away, we did this control experiment where instead of moving beans for 20 minutes, half the subjects had a lexical decision task on the word T-O-W-A-R-D, toward, or an anagram of that word. For 600 trials, they went word, non-word, where it's toward or an anagram. The other subjects had 600 trials of the word away or an anagram of the word away. We then had them do the reading of these same sorts of sentences, judging the meaningfulness, and what you can see is although there is an effect of the lexical decision task, for some reason, having responded to away makes you faster. I have no idea what that's about. But for us, more importantly, this interactive pattern does not appear when we've tried to fatigue a lexical representation compared to when we fatigued a motoric representation. The rest of the experiments are replications of this. Importantly, here's a replication of the abstract sentences. In this experiment 3, these abstract transfer sentences were the only sentences describing action. There were no concrete transfer sentences. So it wasn't like the participants got the idea, oh, this is all about transfer. No, these were the only sentences describing action. A couple other conditions that I won't go through. I'm not going to go through this. I'm just going to get to the conclusions. So, in designing primate action systems, evolution figured out solutions to difficult problems of timing, learning, serial order, hierarchical control, and more. Many of those same problems occur in language, and it appears that evolution adapted mechanisms of action control in Broca's area to language. And so let me now try to answer some of the questions that have been raised. So on the first day, Grimaldi said, what does cognition do? Well, let me offer an answer. What cognition does is to guide action. That's the point of cognition. The point of cognition is not to do language. It's not to do perception. When we perceive things, the reason we're perceiving that is that we are perceiving it in order to control our action. The reason that we are talking is not to entertain ourselves, but to guide the action of others. Cognition is all about action. That's the only story that makes any sense in an evolutionary sense. Evolution would not have allowed us to develop these complex perceptual systems if it didn't contribute to our survival. Are there similarities between manipulation and speech? Yeah. I think that there are huge similarities between manipulation and speech, and it's because they're produced by virtually the same mechanisms. Where does recursion come from? Well, in fact, I don't think that we as humans have a completely recursive system, where we can do things with recursion to any extent that's required by the task. I mean, you all know, for example, how difficult it is to understand center embedded sentences when you have more than one or two embeddings. What I think is happening here, where does recursion come from? Recursion is coming from the hierarchical control of action. And to the degree that our action systems can can generate hierarchies to control action, that's the degree that we have recursion both in action and in language. But language needs a working memory to escape the here and now. How can you escape the here and now when you're talking about these sensory motor representations? I mean, that's, you know, escaping the here and now, that's a primary principle of language. Well, in fact, I think it's not that difficult. First off, this sort of loop between the predictors, between the controller generating a command and then that coming up and the predictor generating a prediction of what's going to happen when that command is executed, that sort of loop is already sort of close to a working memory loop. But more than that, I think what you can see is that the whole point of this sort of model for action control is to predict the future, is to predict what's going to happen several steps down the line. And so it is already a mechanism for escaping the here and now and predicting what's going to happen next. And then, but we already know that sensory motor representations won't do. I mean, we've known that since the middle 50s. Well, I think what we know is that a simple SR system will not do. I don't think we know at all that grounding symbols and sensory motor representations won't do. And in fact, if you focus on meaning, on what language is all about, you almost have to ground those symbols in sensory motor representations. And finally, is a neural theory of language possible? Well, as you might suspect, I think the answer is definitely yes. What I hope to have done here is to at least provide one sketch for how such a theory might look. So, thank you very much.
Well, thank you very much. So I would say just one quick question, and then we have the coffee break, a quick one again. So the first one was actually on the left-hand side, but then there is the coffee break, and we can have other discussion later on.
These the only technical questions?
Yeah.
Technical point. Recursion and hierarchy are two different things. You can have hierarchical structure without recursion. For instance, most of phonology is hierarchical but not recursive. Syllable structures have a hierarchy because you get the whole thing and then its components, but you cannot use a syllable as a constituent of a syllable. So what I'd like to see is if in the case of motor structure, you just get hierarchy or hierarchy with recursion.
In fact, I don't know the answer to that. What I can tell you is within this sort of model, clearly you can get hierarchy, and you can get recursion of a sort, namely recursion of the sort that the mechanisms that go into producing this can then be recursively used to produce another level at the hierarchy. So it's a type of recursion, maybe not completely satisfying to you. I don't know how far we'll be able to push this. Yeah, I appreciate the problem.
Calling back the same entity and then further extending the same entity, essentially, right? So you need an element of the same level that somehow appears on both sides of a rule, essentially. That's
right.
recursion.
That's right. I understand that, and I'm not sure to what extent this model will generate that, but you want to know what else I'm not sure of? I'm not sure how much we need that for human language. I know linguists use that in their description of language, but whether we need recursion in language use, I'm not convinced.
Okay.
Oh, I don't know if we, oh, excuse me. Coffee break.
Yeah, I would propose so because we already have only 5 minutes for the, 15 minutes for the coffee break. So if you want to continue the discussion during the coffee break, and then we have another discussion spot later on. Okay, so please, if you can come back here in like 15 minutes or so. Today we are a bit tight. Okay, thank you very much.